Hi all, welcome back to my channel. Today we are going to see about arrays and strings and C language.
Welcome. Today we're diving into arrays and strings, two fundamental building blocks in programming. We'll explore how they work, why they matter, and how to use them effectively. This session is part of Unit 3, and it's designed to strengthen your understanding of data structures in computer science. Let's get started. Let's talk about arrays, a way to group multiple elements of the same type under a single variable name. Instead of declaring separate variables like mark1, mark2, and so on, we use an array. For example, int marks5 creates a container named marks that can hold 5 integers. This makes managing related data simpler and more organized. Today, we'll explore how to declare and initialize these arrays effectively. Let's talk about what this slide means. Here, int is the data type. It tells us what kind of values we're storing. Marks is the name of the array, and 5 is how many elements it holds. The indexes start at 0, not 1, so marks 0 is the first element, the second, and so on up to marks 4. When we declare an array, we're telling the compiler exactly what type of data we want and how many pieces it should reserve. The syntax looks like this: data type array name, then size in square brackets. For example, int marks5. Let's talk about initialization. That's when we assign values to each element in an array. Here, we have an array called marks with 5 elements. Each position or index holds a specific value. For example, marks at index 0 is 80, index 1 is 75, and so on. This setup lets us organize data in a neat, ordered way. Initialization is the first step to working with arrays, giving each slot a clear, defined value right from the start. Let's look at how we can declare and initialize an array all at once. Here, we create an array called numbers with 5 elements. The declaration is the part where we say what the array is, in this case, 5 integers. The initialization is where we assign values to each element, all in one step. So, we're combining declaration and initialization into a single, clear statement. It's a neat way to set up your array quickly and efficiently. When we initialize an array, we don't always need to specify its size explicitly. For example, if we write int numbers equals curly braces 10, 20, 30, 40, the compiler steps in and figures out the size for us. Here, it counts 4 elements, so it's the same as declaring int numbers with size 4, then listing those values. This makes our code cleaner and less error-prone. The size is automatically determined. Here, we're looking at how arrays can be partially initialized in code. You might declare an array with 5 elements, but only provide values for the first 2. The rest don't stay uninitialized. They automatically get set to 0. So, conceptually, the first 2 spots hold your values, and the remaining 3 are filled with zeros. This is called partial initialization, and it's a handy way to avoid leaving elements with unpredictable data. Let's talk about character arrays. They store individual characters, like letters. For example, you might have an array with 5 characters, A, B, C, D, and E, or you can use a string, which is just a sequence of characters inside quotes, like hello. In C, strings always end with a special character, the null character, written as \0. This marks where the string finishes, so the program knows when to stop reading. It's a simple but crucial detail. Let's talk about two-dimensional arrays, a way to organize data in rows and columns, like a grid. Imagine a matrix with 2 rows and 3 columns. Each spot holds a value, and we access it using 2 indexes, one for the row, one for the column. For example, matrix 0, 0 is 1, while matrix 1, 1 is 5. This structure helps us manage data that naturally fits into tables or grids, making complex information easier to handle. Let's talk about one-dimensional arrays. They're a way to store multiple values of the same type, lined up in a row. For example, when we declare an array like this, int marks with 5 elements, we're setting aside space for 5 integers. The key thing to remember is that indexing starts at 0. So the first element is at position 0, the second at 1, and so on, up to 4 for 5 elements. It's a simple, linear structure, easy to understand and use. Let's talk about traversing an array, a fundamental concept in programming. We usually use a for loop to go through each element one by one. Here, the loop starts at 0 and runs until it reaches 5, printing each value in the array. For example, marks 0 is 80, marks 1 is 75, and so on. If we want just one element like marks do, we can print it directly, which gives us 90. This way, we access and work with each part of the array easily. Here, we have a simple example that finds the sum of numbers stored in an array. First, we declare an array with 5 elements, 10, 20, 30, 40, and 50. Then, we set a variable called sum to 0, ready to accumulate the total. Using a for loop, we go through each element in the array, adding its value to sum. Finally, we print the result, which is 150, the total of all those numbers combined. This is a basic but essential pattern in programming. Let's talk about two-dimensional arrays. Think of them as arrays organized in rows and columns, like a grid or a table. They're perfect for representing matrices or any data that fits neatly into rows and columns. When we declare one, like int matrix 2 by 3, it means we have 2 rows and 3 columns. That gives us a total of 6 elements, 2 times 3. It's a simple structure, but incredibly useful. Here, we're looking at a two-dimensional array, or matrix. In C, it's declared as having 2 rows and 3 columns. The initialization fills it with 6 values, arranged in 2 sets of 3. Visually, you can think of it as a grid, 2 rows down, 3 columns across. Each number sits at the intersection of a row and a column, making it easy to access any element by its position. This setup is foundational for working with matrices in code. Let's take a closer look at how we access elements in a matrix. We use 2 indices. The first is the row, the second is the column. For example, matrix 00 points to the element in the first row and first column, which is 1. Matrix 01 is the first row, second column, that's 2. Remember, this notation helps us pinpoint any value in a grid-like structure, row by row, column by column. It's the foundation for working with matrices. When we work with rows and columns, nested loops are our go-to tool. Here, the outer loop runs through each row, while the inner loop steps through each column within that row. This way, we visit every element in the matrix, one by one. After printing all columns in a row, we move to the next line, making the output easy to read. This pattern is how we traverse a two-dimensional array efficiently and clearly. In C, strings aren't a separate data type like in Java. Instead, they're just arrays of characters. For example, if we declare a name with 6 characters to hold hello, it actually stores each letter plus a special null character at the end. This null character, written as \0, tells the program where the string ends. So even though hello has 5 letters, it needs 6 spaces in memory to include that invisible end marker. Let's talk about declaring character arrays in C. When you write char name with a size of 20, you're reserving space for up to 19 characters. Because the last spot is always for the null terminator, that special character that marks the end of the string. You can also initialize a string like this, char name equals Kumar. Here, the compiler figures out the size for you. Conceptually, each letter gets its own index, and the string ends with that crucial null character. Let's talk about using scanf to read strings in C. Here, we declare a character array called name with space for 20 characters. When we use scanf with %s, it reads input until it hits whitespace. So if the user types Kumar, it stores that in name. But if they type Kumar Kumar, only the first Kumar is captured. That's because %s stops reading at the first space. It's a simple way to get a single word but not a full sentence. When we need to read strings that include spaces, fgets is our go-to function. Unlike some other methods, fgets reads the entire line, spaces and all, making it safer for names or phrases. Here, we declare a character array to hold the input, then call fgets with that array, its size, and standard input. This way, if someone types Kumar Kumar, we capture the full string without cutting it off. It's a simple but important step for handling user input correctly. In C, working with strings is made easier thanks to a set of built-in functions found in the StringH library. These functions cover the essentials, measuring string length, copying one string to another, joining strings together, comparing them, and searching within them. Together, they form the foundation for handling text in C programs, letting us manipulate strings efficiently without reinventing the wheel every time. Let's talk about how to find the length of a string in C. The function we use is strlen. It counts the number of characters in a string, but it doesn't include the null terminator, that special character that marks the end. For example, if we have the word hello, strlen will return 5 because it counts just the letters. This is a simple but essential tool whenever we need to know how long a string really is. Let's break down how strcpy works conceptually and in code. Imagine you have a source string like hello. When you use strcpy, it copies that exact string into a destination. The syntax is straightforward. strcpy takes the destination first, then the source. So if source holds hello and destination is an empty array, strcpy fills destination with hello. It's a simple but powerful way to copy strings in C. Let's talk about concatenation, a simple way to join two strings into one. Here, we start with two separate pieces, hello and world. Using the strcat function, we combine them into a single string, hello world. It's like snapping two puzzle pieces together to make a complete picture. This technique is fundamental in programming when we want to build or modify text dynamically. The example shows how strcat takes the second string and appends it to the first, changing the first string in the process. When comparing strings in C, you can't just use the double equals sign. That only checks if the two pointers point to the same memory location, not if the strings themselves are equal. Instead, we use the function strcmp. It compares the actual characters in the strings. If the result is 0, it means the strings are identical. So here we see two arrays holding hello. Using strcmp confirms they match, and we print strings are equal. This is the proper way to compare strings in C. Let's look at an example with the strcmp function. When we compare apple and banana, strcmp returns a negative value. That's because apple comes before banana in dictionary order or lexicographically. The function's result tells us how the two strings relate. 0 means they're equal, less than 0 means the first string is smaller, and greater than 0 means the first string is larger. This simple return value packs a lot of meaning for string comparison. Let's talk about strchr. This function searches for a specific character inside a string. For example, we have the word computer. When we call strchr with the letter P, it returns a pointer to the first place P appears in that string. It's a simple but powerful way to locate characters quickly, especially when you need to work with parts of a string starting from that point. Let's talk about str. It's a function that looks for one string inside another. Here, we have the text, I love programming. When we use str to search for programming, it finds exactly that word inside the bigger string. It returns a pointer to where that substring starts. So, str is a simple but powerful way to locate smaller pieces of text within larger ones. When working with strings in programming, there are a handful of functions we rely on again and again. strlen helps us find the length of a string, how many characters it contains. strcpy lets us copy one string to another. strcat joins two strings together like glue. strcmp compares two strings to see if they're the same. strchr searches for a specific character inside a string. And strstr looks for a smaller string within a larger one. These functions form the backbone of string handling. Here, we're looking at a simple C program that compares two strings. It uses the strcmp function. If the strings are the same, it prints equal. Otherwise, it prints not equal. Then, it shows how to find the length of a string, copy one string into another, and finally, concatenate two strings together. This example highlights some basic but essential operations when working with text in C. In C, strings aren't a separate data type. Instead, a string is just an array of characters. So when we talk about an array of strings, we're really dealing with a two-dimensional character array. For example, if we declare char names with 5 rows and 20 columns, that means we can store up to 5 strings, each up to 19 characters long plus the null terminator. Conceptually, each row holds one string, like names 0 holding Aaron, names 1 holding Bala, and so on. Here, we have a simple example of how to initialize and access elements in a two-dimensional character array. We've created an array called names, holding 5 strings, each up to 20 characters long. To get a specific name, like the third one, we use print with the index 2, since counting starts at 0. That prints Kumar to the screen. This shows how arrays store and retrieve multiple pieces of text efficiently in code. Here, we're looking at a simple C program that reads and prints an array of strings. The code declares a two-dimensional array to hold 3 names, each up to 19 characters long. Then, it uses a loop to read input safely, making sure not to overflow the buffer. Another loop prints each name on its own line. This is a basic but effective way to handle multiple strings in C, showing how arrays and loops work together. Sorting is all about putting things in a specific order. Imagine you have a list of numbers, 50, 20, 40, 10, 30. When we sort them in ascending order, they become 10, 20, 30, 40, 50. One of the simplest ways to do this is called bubble sort. It's a straightforward method that compares and swaps numbers step by step until everything's in the right place. Sorting helps us make sense of data and find what we need faster. Let's break down the basic idea behind bubble sort. We start by comparing 2 elements right next to each other. If the first one is bigger than the second, we swap them. Then, we move on to the next pair and do the same. We keep repeating this process, bubbling the largest values to the end with each pass. It's simple, but effective, a foundational sorting method that helps us understand more complex algorithms. Here, we're looking at a simple program that sorts an array of numbers. It uses a classic method, comparing pairs of elements and swapping them if they're out of order. This process repeats until the entire array is sorted from smallest to largest. At the end, the program prints the sorted array, showing the numbers neatly arranged. It's a straightforward example of how sorting algorithms work under the hood. Here, we see a simple way to sort an array of strings using C. The key functions are strcmp, which compares 2 strings, and strcpy, which swaps them when needed. The nested loops go through the array, comparing each pair and swapping them if they're out of order. By the end, the array is sorted alphabetically. Finally, the program prints each name in order, showing the result of the sorting process. This is a classic example of how to handle strings in C. Here, we see a list of names: Arun, Bala, Kumar, Ravi, and Vijay. The key point is the function strcmp, which compares 2 strings. In this case, it's checking the order between names at positions J and J+1. This comparison is essential for sorting or organizing the names correctly. It's a small but powerful step in managing text data efficiently. When we talk about searching, we mean checking if a specific element is in a list or array. One straightforward way to do this is called linear search. Imagine we have the numbers 10, 20, 30, 40, and 50, and we want to find 30. The algorithm looks at each number one by one, first 10, then 20, and when it reaches 30, it stops. It's simple but effective for small or unsorted lists. Here, we have a simple linear search program in C. It goes through an array of 5 numbers, looking for a specific value, in this case, 30. If it finds the value, it prints the index where it's located and stops searching. If it doesn't find the value at all, it lets us know by printing element not found. This is a straightforward way to search through a list, one element at a time. When we talk about linear search, the key point is how long it might take to find what we're looking for. In the worst case, the element we want could be at the very end, or not there at all. That means we have to check every single item in the list. So the time it takes grows directly with the number of elements. We call this O of n, a simple way to say it scales linearly with the size of the data. Here, we're looking at a simple program that searches through an array of strings. Notice how it uses strcmp to compare each name with the key, because with strings, the usual equals sign won't work. The loop checks each element, and if it finds a match, it prints the index and stops searching. If no match is found, it lets us know. This is a straightforward way to find a string in a list. When we talk about matrices in programming, the natural way to represent them is with a two-dimensional array. Think of it as a grid, rows, and columns, just like a spreadsheet. For example, in the C language, you can declare a 2x2 matrix using nested braces. Each inner set represents a row, so here we have the numbers 1 and 2 in the first row, 3 and 4 in the second. This setup makes it straightforward to perform matrix operations. We can only add two matrices if they share the same dimensions. That means the same number of rows and columns. When that's true, we add corresponding elements together, one by one. It's a straightforward process, but it only works when the matrices line up perfectly. This slide shows a clear example of how matrix addition looks in practice, helping us see the rule in action. Here, we see a simple program that adds two 2x2 matrices. The code starts by defining the matrices A and B with their values. Then, it creates a new matrix C to hold the results. Using nested loops, it adds corresponding elements from A and B, storing the sums in C. Finally, it prints out the resulting matrix, showing the combined values. This example illustrates how we can work with multi-dimensional arrays and loops to perform basic matrix operations in C. The same idea applies when we subtract matrices. We take each element from matrix A and subtract the corresponding element from matrix B, so, for any position in the matrix, the result is simply O at that spot minus B at that spot. It's a straightforward element-by-element process, just like addition, but with subtraction instead. This keeps things consistent and easy to follow. Now we're shifting gears to something a little different: matrix multiplication. It's a fundamental operation in math and computer science, but it's not just about numbers. It's about transforming data, combining information in powerful ways. Understanding this helps us unlock new possibilities, whether it's in graphics, machine learning, or solving complex problems. Let's dive in and see how it works. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. Here, we see a simple C program that multiplies two 2x2 matrices. It initializes matrices A and B with fixed values, then calculates their product, storing the result in matrix. See the nested loops handle the multiplication and addition for each element. Finally, the program prints the resulting matrix to the console. This example shows how basic matrix operations are implemented in code, combining loops and arithmetic to solve a common problem. To transpose a matrix, we flip its rows and columns. That means the element in row I, column J, moves to row J, column I. It's a simple swap, turning rows into columns and columns into rows. Here, you can see the example and the resulting output after the transpose operation.
Thank you for watching my videos. For more videos, please do like, share and subscribe my channel.